Have you ever wondered where this seemingly infinite universe is heading? Will it keep expanding forever or face some kind of ultimate transformation? Today, we're embarking on a mind-blowing journey to explore one of the most dramatic theories about the end of the universe, the Big Rip. Since the Big Bang 13.8 billion years ago, our universe has been continuously evolving. Galaxies formed, stars were born and died, and life emerged and thrived on Earth. But like every story must eventually come to an end, the story of the universe is no exception. It, too, will one day reach its conclusion. Scientists have proposed several theories about the ultimate fate of the universe. Some predict that the universe will end in a big crunch, collapsing back into a single point. Others suggest it will undergo heat death, reaching a state of thermodynamic equilibrium and eternal stillness. And then, there are even more extreme and mind-bending possibilities. But in today's video, we're focusing on one of the most dramatic and mind-blowing theories, the Big Rip. This theory doesn't just describe the end of the universe. It envisions a complete, all-encompassing destruction, from the largest cosmic structures to the smallest particles. Imagine this. Not only will galaxies be torn apart, but even atoms themselves will be ripped into fragments. In the time ahead, we'll dive deep into this fascinating theory, uncovering its scientific foundation and exploring the profound impact it has on our understanding of the universe and existence itself. Let's start in 1929. That was the year when astronomer Edwin Hubble made a groundbreaking discovery that forever changed our understanding of the universe. By observing the light spectra of distant galaxies, he uncovered a remarkable phenomenon. All these galaxies are moving away from us, and the farther a galaxy is, the faster it is receding. This phenomenon can be explained using the Doppler effect. Just like the pitch of a siren drops as an ambulance moves away from you, the light emitted by galaxies receding from us shifts toward the red end of the spectrum. This is what's known as the famous redshift phenomenon. Hubble's discovery revealed something groundbreaking. The universe is expanding. It's like a balloon being blown up, where every point on the surface moves farther away from every other point. But this wasn't the most shocking revelation just yet. In 1998, two independent research teams, observing Type Ia supernovae, uncovered an even more perplexing phenomenon. The expansion of the universe isn't slowing down due to gravity. Instead, it's accelerating. This discovery completely upended our expectations and reshaped our understanding of the cosmos. To explain this accelerated expansion, scientists introduced the concept of dark energy. Dark energy is a mysterious force with a negative pressure property, creating a repulsive effect that drives the universe to expand faster and faster. What's truly astonishing is that dark energy makes up about 68% of the universe's total energy density, making it the dominant component of the cosmos. Let me give you a more intuitive analogy. If the universe were a pie, the ordinary matter we're familiar with, including all stars, planets, and galaxies, would make up just about 5% of it. Dark matter would account for approximately 27%, while dark energy takes up the remaining 68%. We are living in a universe primarily composed of elements we cannot directly observe or fully understand. An unseen, mysterious majority governs the cosmos we inhabit. As the universe expands, the density of both matter and dark matter decreases. However, the density of dark energy might remain constant, or even increase. This suggests that, over time, the influence of dark energy will grow stronger and stronger, eventually dominating the fate of the cosmos. This forms the foundation of the Big Rip theory. If dark energy continues to grow stronger, its repulsive force could eventually overcome all other forces, including the strong nuclear force, weak nuclear force, and electromagnetic force. In this scenario, everything in the universe, galaxies, stars, planets, atoms, and even subatomic particles would be torn apart. Now, let us embark on an imagined journey through time, traveling into the distant future to witness the process of the Big Rip with our own eyes. Remember, this is not just the separation of galaxies, it is a complete tearing apart, from the largest scales to the smallest. First, let us begin with the largest scale, the galaxy clusters. Under normal circumstances, galaxy clusters are massive structures held together by dark matter halos and the force of gravity, containing hundreds or even thousands of galaxies. However, as the density of dark energy continues to increase, the repulsive force it generates will eventually surpass the binding force of gravity. Imagine the Virgo cluster, which contains at least 300 galaxies and is located about 54 million light-years away from us. In the early stages of the Big Rip, this enormous structure would begin to disintegrate. The distances between galaxies would grow larger and larger until they lose their gravitational connection to one another. Interestingly, our Milky Way and the Andromeda Galaxy are originally expected to collide in about 4.5 billion years. However, under the scenario of the Big Rip, the repulsive force of dark energy might prevent this cosmic collision. Instead, as the two galaxies approach each other, they would be pushed apart, driven away by the ever-increasing power of dark energy. Next, the claws of the Big Rip will extend toward individual galaxies. Take our Milky Way as an example. It contains roughly 400 billion stars, bound together by gravity and a dark matter halo. However, when dark energy becomes sufficiently powerful, even this galactic-scale gravitational binding will be broken apart. The Milky Way's beautiful spiral arms would begin to unravel. Stars would be flung out one by one, breaking free from the galaxy's gravitational grasp, like droplets flung outward from a whirlpool. The once orderly systems of stars that orbited around the galactic center would become wanderers, drifting alone in the ever-expanding emptiness of space. Then, the reaping process becomes even more personal. It targets stellar systems. Our solar system, this place we call home, would not be spared. First, the outer planets, Neptune, Uranus, Saturn, and Jupiter, would be torn away from the Sun's gravitational influence, flung into the vastness of expanding space. Earth's orbit would become unstable. Our blue planet might be flung into the freezing void of interstellar space or pulled toward the Sun, ending its story in a fiery inferno. In either case, the conditions for life would vanish. But the tearing will not stop there. It will delve deep into the core of the star. The existence of a star is sustained by the balance between the radiation pressure produced by nuclear fusion in its core and the gravitational force. When the repulsive force of dark energy becomes strong enough, it will break this delicate balance. The Sun and other stars will begin to expand and collapse. Nuclear fusion reactions may spiral out of control or cease entirely. One by one, stars will extinguish in the cosmic night sky until the universe descends into complete darkness. Ultimately, the Big Rip will penetrate to the most fundamental level of matter, the atom. Under normal circumstances, atomic nuclei are bound together by the strong nuclear force, while electrons orbit the nucleus due to the electromagnetic force. These are among the most powerful forces in nature. But if dark energy continues to intensify, it could eventually overcome the strong nuclear force. Imagine even the protons and neutrons within atomic nuclei being torn apart. This would mean that the basic building blocks of matter, forming our bodies, the Earth, the stars, and the entire universe, would disintegrate. In the final stage of the Big Rip, even protons and neutrons would be torn apart into their most fundamental constituents, quarks and gluons. Ultimately, the universe might be left with nothing but elementary particles drifting alone in an ever-expanding spacetime. This is the ultimate form of the Big Rip. A completely disassembled universe, devoid of stars, planets, atoms, or even atomic nuclei. Only fundamental particles remain, drifting farther and farther apart in an infinite and desolate void. Now you might wonder, when will this apocalyptic scenario occur? This is a crucial question, and the answer largely hinges on the nature of dark energy, one of the greatest enigmas in modern physics. According to the current dark energy models, if the density of dark energy remains constant, a model known as the cosmological constant, the Big Rip may never occur. The universe would continue to expand, but the tearing force would never become strong enough to overpower other fundamental forces. However, if dark energy is dynamic, meaning its density increases over time, the situation changes entirely. Some models, referred to as phantom dark energy, predict that the density of dark energy would continually grow, eventually leading to the Big Rip. In these models, the Big Rip could occur in about 22 billion years. Sounds distant, doesn't it? But let's place this timescale in the context of the universe's overall history. The universe is currently about 13.8 billion years old, so 22 billion years means it has roughly 1.6 times its current lifetime remaining. Let's take a closer look at this timeline. Approximately 1 billion years before the Big Rip, galaxy clusters would begin to disintegrate. Round 60 million years prior, individual galaxies would separate. In the final few months, stellar systems would fall apart. During the last 30 minutes, stars and planets would be torn apart. And within the final 10-12 seconds, even atoms themselves would be broken down. So, does our current observational data support this scenario? Using data from the Planck satellite, the Hubble Space Telescope, and ground-based observatories, we can measure the history of cosmic expansion and the properties of dark energy. Current observations indicate that the behavior of dark energy aligns more closely with a cosmological constant rather than phantom dark energy. However, our measurement precision is not yet sufficient to fully rule out the possibility of a Big Rip. Future observational missions, such as the Euclid Space Telescope and the Nancy Grace Roman Space Telescope, will provide us with much more precise data. If the Big Rip were to occur, any intelligent life in the far future would face the ultimate challenge. Could they find a way to escape such a cosmic-scale catastrophe? Or perhaps, could they reach a level of understanding and technological advancement where they might manipulate dark energy itself? These are fascinating questions to ponder. Of course, the Big Rip is not the only possible fate of the universe. Let's take a brief look at several other major theories about the end of the universe so that you can compare their characteristics. First is the Big Crunch. In this scenario, the expansion of the universe will eventually stop and reverse. All matter will begin to move closer together until the universe collapses into a point of infinite density, potentially leading to another Big Bang. This represents the concept of a cyclic universe. Another theory is heat death or the Big Freeze. In this scenario, the universe will continue to expand and cool until it reaches thermodynamic equilibrium. All differences in energy will disappear, entropy will reach its maximum, and no organized processes can occur anymore. The universe will become a cold, dark, and lifeless place. There is also the false vacuum decay theory, which suggests that we currently exist in an unstable vacuum state. If the vacuum undergoes a phase transition, it would create a destructive bubble expanding at the speed of light, altering the very laws of physics. These different theories about the end of the universe led us to ponder a profound philosophical question. What is the meaning of our existence in a finite universe? If everything ultimately comes to an end, do our lives, civilizations, and achievements still hold value? The Big Rip theory is particularly dramatic because it does not merely predict the end of the universe's structure, but also the breakdown of matter itself. It reminds us that everything we know, from galaxies to atoms, might be far more fragile and transient than we imagine. Yet perhaps it is precisely this finiteness that makes our existence so precious. Every moment, every stargazing experience, every scientific discovery holds unique value in this universe that may not last forever. Alright, if you enjoyed today's content, don't forget to like, subscribe, and click the bell icon to turn on notifications. We have more exciting cosmic exploration content coming your way next week.